Hello everyone, today we're going to talk about the discrete Fourier transform. The prerequisites for this material are calculus, linear algebra, Fourier series, and the sampling theorem. The discrete complex sinusoids, we already talked about them when we talked about sampling, are n-dimensional vectors which have this entry j that goes from 0 to n-1, and they're indexed by another variable k, which represents the frequency and which also goes from 0 to n-1. And notice that here, this is a complex exponential, we have n down here, so this expression is actually periodic in both j and k with period n, because the complex exponentials are periodic. So you have complex exponential is periodic with period 2 pi. But here I want to emphasize that we are looking at the case where j and k just go from 0 to n-1. Okay? So in that case we have n-dimensional vectors, and these guys are orthogonal and their norm is equal to square root of n. So if we scale them by 1 over square root of n, we get an orthonormal basis of n-dimensional vectors. This is what these guys look like. These are the entries j. Here k is equal to 2 and n is equal to 10. So it's a 10-dimensional vector. There's 10 of those. This for k equals 2, this for k equals 3. And as you can see, as k changes, the frequency of the discrete sinusoid changes. It depends on k. Remember that this corresponds to the real part and this corresponds to imaginary part. And this continuous line corresponds to the continuous sinusoid. We can interpret these discrete sinusoids as samples of continuous sinusoids, but that's not the only way of interpreting them. You can also interpret them as n-dimensional vectors in their own right. Okay, so the discrete Fourier transform is obtained by taking the inner product of a vector of dimension n with this n different discrete sinusoids. So here we can express this as a matrix, which is called the DFT matrix, where each row is the complex conjugate of one of these discrete sinusoids. Okay? Realize that we're taking the inner product with orthogonal vectors, so this is nothing else than a change of basis of the vector. In that sense, you can think of this as rotating the vector so that now, in its new representation, the axes align with discrete sinusoids. This rotation is of course invertible because it's a rotation, because again we have this family of orthogonal vectors. We have to be a little bit careful because here each of the rows actually has norm square root of n. So if you want to invert this rotation, you have to divide by n. So again, we can invert the DFT by just applying the adjoint of this matrix. Why? Because the rows of this matrix are orthogonal vectors, so that if we scale it by 1 over square root of n, which is the norm of each of those rows, you get an orthogonal matrix such that this guy times its adjoint is just equal to the identity. So now, if I have a vector x and I compute its DFT, if I apply the inverse DFT to x hat, again it's just the adjoint, which is the transpose and taking complex conjugate, if you remember your linear algebra, this, which I'm going to call maybe y, oh, actually sorry, what I meant is this. What I meant is, so okay, so now I have the DFT, now I'd say y is equal to 1 over, so the inverse, what we call the inverse DFT of x hat, well, this is just equal to 1 over n f, like the adjoint of fn times fn, but this guy is the identity, and this would be multiplying x, so it's just equal to x. Okay, so we can easily invert the DFT matrix by applying the adjoint of that matrix multiplied by 1 over n. Again, the DFT matrix is just a rotation, so it's very natural that you can just rotate back easily. By a rotation, I mean an orthogonal transformation. Okay, so now we have been, now when I say, it's an orthogonal transformation, you're just changing the axis. I'm talking about the DFT in terms of n-dimensional vectors, but of course, it also has a really important interpretation in terms of band-limited signals, which is that if you interpret this vector to which you are applying the DFT as containing samples of a band-limited signal, such that it has been sampled respecting the Nyquist theorem, then taking the DFT is the same as taking the Fourier series coefficients of the function. And this is really important because that is what happens when we apply the DFT to sampled signals, such as audio signals or the electrocardiogram that I showed you in the last videos and in the notes. So when I was showing you like the Fourier series coefficients of that electrocardiogram, essentially what I was doing is I was taking samples, applying the DFT, and that's exactly equivalent to computing the Fourier series coefficients. As long as you respect the Nyquist theorem, of course. So just a quick reminder, you should go back and look at the video on sampling if you don't remember this, or look at the notes. But the point is that we have this continuous band-limited signal, and we sample it at some discrete locations. I'm sorry about the notation, by the way, because this guy is now a discrete. So I've been using x to denote an n-dimensional vector in this particular slide, because it's a slide that I took from the sampling notes, from the sampling slides. This guy is actually a continuous signal, so I apologize for that. But anyways, we're taking n samples from that continuous signal. That continuous signal is a linear combination of of continuous sinusoids, because that's the definition of band-limited signals. When we sample, though, it becomes a linear combination of discrete sinusoids. So we can write it as this linear combination of discrete sinusoids, where the weights here, the coefficients corresponding to the discrete sinusoids, are just the Fourier series coefficients. Okay? As a result, when we take inner products with the discrete sinusoids, what happens is that this is the same as taking inner products with each of the discrete sinusoids, but only one of those inner product is non-zero, because this is an orthogonal family of functions as long as we are respecting the sampling theorem, and we get the Fourier coefficient back. Okay, and notice that this is inner products with discrete sinusoids. It's just applying the DFT to the vector of samples. Again, go back to the video on sampling if this is not super clear, but I just wanted to remind you that the DFT is directly connected to sampling. And the idea that you should keep in your minds is that if we have sampled according to the Nyquist theorem, applying the DFT to a vector of samples extracts the Fourier series coefficients of the underlying continuous signal, as long as, again, that continuous signal was band-limited and we're sampling according to the Nyquist theorem. Okay, so now that we have defined what the DFT is and we have connected it to sampling of continuous signals, let's turn to the question of, how computationally expensive is it to compute the DFT. This is a topic of huge importance, because when we're doing signal processing or audio processing and so on, we apply DFTs all over the place to really, really large signals, signals with many, many, many entries. Because remember, for example, that when you sample audio, you want to sample it like at 44 kilohertz. So you have, 40,000 samples per second. So you're sampling this at a really, really high rates. So you get like really, really long vectors. and you need to apply, if you want to process them in the frequency domain, which you always want to do when you're talking about audio, you need to do this really efficiently. We're also going to see that the DFT is very useful for analyzing images, and images have many, many pixels. So you want to be able to apply the DFT very efficiently. The bad news is that if you just compute the DFT naively by multiplying this n times n DFT matrix with the n-dimensional vector, then the complexity, of course, is n squared, because you have n rows, and for each row you're multiplying n numbers and adding them up. So your complexity is n squared, and this is way too large. Like, this would be super, super slow if we just did this for these large signals that I have just mentioned. Luckily, you can exploit the structure of the DFT matrix to do much, much better. And that's called, the algorithm that exploits this is called the fast-Fourier-transform. It has been called by Gilbert Strang as it has been described as the most important numerical algorithm of our lifetime. So it's really a big deal. The main insight is that if you look at the n times n DFT matrix, you can express it in terms of n half times n half DFT matrices, which allows you to define a recursive algorithm to compute the DFT much more efficiently. Okay, so let's explain this in detail. We're going to separate the n times n. So this is an n times n DFT matrix. Okay, n times n. Oops. Okay, so maybe I should have, that was maybe confusing, n times n. Okay, it's an n times n DFT matrix, and now we're going to separate it into sub-matrices. I'm going to show that they have very special structure. In particular, we're going to cut it in half here, okay, where this is n half and this is n half. Okay, we're going to do that, and we're also going to separate it according to even. The reason why I'm calling this even is because here, okay, 0. I'm going to number the rows like that up to n minus 1. I'm going to extract the even columns, and I'm going to separate them from the odd columns. Okay, this divides the top half into two different submatrices, and I'm going to do the same for the bottom. I'm going to extract the even columns. By even, I mean according to this index here. And I'm also going to extract the odd columns. Okay, so I've divided the n times n Fourier matrix into 4 submatrices that I've colored here to make it clear. Okay, and we're going to use, I'm assuming, by the way, that n is even. So I have the same number of even columns as odd columns. This is just for simplicity. Okay, so this is the picture. This is the n times n DFT matrix, and I've divided it into this top half, the bottom half, and I've also divided it according to the even columns, because remember, I'm calling those the even columns because we start at 0, and the odd columns. Okay. Now the insight here is that if I'm looking at this x hat, that is equal to the matrix times x, realize that the 0th entry is only applied to the 0 column. Entry 1 is applied to column 1. So when we can decouple this into, just by linear algebra, by the way. So if we call this column 0, column 1, and so on, we can write it as Cj, xj, okay, where these are actually vectors of dimension n, which correspond to the columns. And now I can just separate this into, sorry again for my handwriting. I think I can't finish one of these videos without apologizing for my handwriting. Okay, so this is even j, and this is odd j. Okay. So we're going to separate this, and now we can look at the submatrices separately. When you do that, it turns out that you can obtain the odd submatrices from the even submatrices by just multiplying each of the even submatrices by a single number. So this guy is going to multiply this, and you're going to get this column of the odd submatrices. This is not immediately obvious, but if you check, you will see that that is the case. You will do this in detail in the homework, or you can check the notes. But for the sake of this video, we're just going to use the fact directly. Okay, so I can change the even columns into the odd columns by just applying a single number to them. This is a diagonal matrix, okay? In addition, it turns out that the top even columns are exactly the same as the bottom even columns, exactly the same, and they're both equal to an n-half times n-half DFT matrix. This is very cool because now when I look at, so this is x hat, this is even entries, and these are the odd entries. So the even entries get multiplied by these submatrices. These are the top ones and these are the bottom ones, but these guys are the same. So now I can just apply, you know, these are the top entries that I'm, the top half of the entries, and these are the bottom half of the entries. I'm applying exactly the same matrix to apply to obtain each of them, because this guy is exactly the same as this guy. Again, I do want to remind you what I'm talking about. So if I have the whole DFT matrix, okay, this submatrix of top even columns is exactly the same as this submatrix of bottom even columns, and they're both equal when I put them together to an n-half times n-half DFT matrix. Okay, that's what I'm saying. We also said that these odd columns, okay, these odd columns, which are these guys, these odd columns, can be obtained from the, maybe I'll do blue, from the even columns by just weighting them by certain numbers. So this means that when we look again at how we're computing the DFT coefficient from the entries of x, so these are even entries, maybe I should use the same color, right? These are the even entries of x, and these are the odd entries of x. Here we're applying the even submatrices, which are both the same. Here we're applying the odd submatrices, but we can obtain them. So this would be the odd submatrices, but we can obtain them from the even submatrices by just multiplying by this diagonal matrix. So how we have managed to express this matrix vector multiplication, where we're multiplying the DFT matrix times this n-dimensional vector, we have managed to express that in terms of smaller DFT matrix, in particular DFT matrix that are half the size. They're n-half times n-half. Okay, each of them, okay, each, like basically we have these 4 DFT matrices, but notice that we just need to apply them, we're applying them to n-half vectors. But now I want you to notice that this guy and this guy is the same, okay, because these are the odd entries, and this guy are the same. So basically, we're just taking 2 matrix vector multiplications, the n-half times n-half DFT matrix. Okay, I feel that this is getting too cluttered. Let me, take a step back. So what is happening here? We have that the DFT coefficients can be computed from the entries of x by taking the product of an n-half times n-half DFT matrix times the even entries. So notice that these two are exactly the same vector. taking the n half times n half DFT matrix of the odd entries, these two guys are again exactly the same, you have to weight the odd entries by certain numbers, and then you add everything together. Okay, like this, you can compute the n times n DFT matrix using only n half times n half DFT matrices. And this is what gives you the recursive Cooley-Tukey Fast Fourier-Transform. You take the Fourier transform, the DFT transformation of the even entries. You take the DFT transformation of the odd entries. Okay, that's a much smaller DFT transformation. And then you combine them by weighting the odd entries and summing everything together. Okay. Then to obtain the n half times the n half DFT DFT transformation of the even and odd entries, you just apply this recursively again and again and again until you're down to so then, you know, with this you would need n fourth times n fourth DFTs. Then in order to compute those, you would need like n eighth times n over 8 times n over 8 DFTs, and so on and so forth. We can show that as a tree diagram, where here this would be the n times n DFTs. You can do that with 2 n half times n half DFT. Those you can do with 4 n over 4 times n over 4 DFTs, and so on and so forth. Okay, so as you can see, this is just a recursive algorithm where here at the bottom you would just have like 1 times 1 DFTs, but many of them, and you recombine them in this way until you build up to the n times n DFT. Okay, this is the recursive fast Fourier transform algorithm. The question is, do we gain anything by computing this recursively like that, as opposed to just applying the matrix vector multiplication? So let's see. In order to analyze this, we're going to, In order to analyze this, we're going to assume that n is equal to L, okay, where L is just a positive integer. So here we have 1, 2, down to L levels. And now we're going to see how many nodes we have at each level. So here in the first level we have 2 nodes that get combined. We're combining 2 n half times n half vectors into the result, which is a length n vector. Here we have 4. Here we have 8. And so on and so forth. So basically there are 2m nodes, as we go down. Now we have to see how much work are we doing at each node. At each node, we're scaling a vector of dimension 2l minus m. So up here we have vectors of length 2, basically n half times n half, which is equal to 2 to the L, which is equal to n minus 1 divided by 1. Okay. In case you're wondering of where the minus m comes from, here it would be n fourth, so it's equal to 2 to the L minus 2, and so on and so forth. Okay, so in general we have 2 to the L minus m. Like that's the dimension of each of the vectors. Remember that in each of these, like in the recursion, what we're doing is we're just adding these vectors up and multiplying by a single number. So the complexity is actually just 2 to the L minus m at each node. But of course, we have a growing number of nodes as we go down. So the complexity at each node is just going to be 2 to the L minus m. And now the complexity at each level is we have to multiply the number of nodes by the complexity at each node, okay? So up here we have only one node, but the complexity is higher because we're adding up 2 n over 2 vectors. Here we're adding up 4 n over 4 vectors. So actually this already kind of tells you what the complexity is going to be, because so realize that at this level, okay, I'm going to again erase everything because I feel that this looks very complicated. But the point is that we have established that here we're adding 2 n-half vectors and weighting them, but that's not too important. Here we have 4 nodes, and the vector at each node is of length n over 4. Here we have 8 nodes, and the vector at each node is n over 8. So it turns out that the complexity at each level is equal to n. Okay, the operations of this recursion at this level, as we build up to the n-dimensional vector, basically the complexity is n at each level. And the number of levels is L, which is equal to the logarithm of n. Okay, so the whole complexity is going to be n log n. Again, let's go back. This is just like, I just wanted to show it on the graph because it's just so much easier to see what's happening. So how much work are we doing here? We're combining 2 n-half vectors, so the work is of order n. Here we're combining 4 n over 4 vectors, so the work is, again, the complexity is order n. Here we're combining 8 n over 8 vectors, so the complexity is n. There's L levels where L is equal to log n, so the whole complexity is n log n. More formally, we have at each level 2m nodes. At each node we scale, we're manipulating vectors of 2l minus m. We have to multiply this and this, so the complexity at each level is 2 to the L, which is n, which is just what I just showed you on the graph. So the overall complexity is n log n, which is dramatically lower than n squared. And in fact, I did a very simple experiment on my computer where I noticed that this is logarithmic, okay? So I checked vectors of length 100, 1000, 10,000, and this is by no means rare. I mean, like when you take samples of sound signals, the vectors are much longer. So you will have to compute DFT transformations of much longer vectors. And again, we also want to apply this to images where there's many pixels. And here you can see the running time in seconds, where this is also logarithmic. This line here is what happens when you apply the FFT, the recursive algorithm. Maybe I should have drawn that in. Let me draw that in. Yeah, maybe this color. Okay. And this is the line that you see if you just apply a naive matrix vector multiplication, and it's much more expensive, orders and orders of magnitude. So here we're almost at 1/10 of a second, whereas for the FFT matrix for 10 to the 4 vectors, we're still under milliseconds. Notice, by the way, this weird pattern that you see here, like this. This is because it's actually, sometimes it may be faster to apply the FFT transformation if the length of the vector is close to a power of 2. And this has to do with the fact that the algorithm works like that, by dividing things in halves. So what have we learned? We have learned the definition of the discrete Fourier transform, and we have learned how to compute it very efficiently using the fast Fourier transform. Thank you very much.